You're listening to the Talking Air Filtration podcast, where you get to know the people that make air filtration possible and help us all breathe easier. Because clean air matters.
We'll get insights from air filtration professionals and learn how they became successful in their careers. Along the way, we will discuss best practices, guidelines, trends, and challenges in air filtration in a variety of applications. We hope HVAC, air filtration, and indoor air quality pros, including business development, engineering, building owners, and facilities management, will enjoy the insights our guests will bring to this podcast.
Nanofiber technology has revolutionized industries from material science to medical devices and are now increasingly being deployed in air filtration. Jon Rajala of AAF Flanders is here with us today to explore the development of the nanofiber market from its inception and academia to modern-day applications for air filtration. Please welcome Jon to the stage.
Thanks, everyone. Thanks for coming to see me talk, and thanks to NAFA for inviting me to speak on nanofibers. When Hunter was telling me he wanted to have a presentation about nanofibers, he asked me because he knew my background in grad school, and I said, I know some other people that can probably talk to better about this, but he insisted I come up here and talk. So hopefully I do a good job. And I know Susan had a great talk this morning, and I don't know if I'll be as dynamic or exciting as her. I'm just a researcher nerd, but we'll try to do what we can, and hopefully I'll be informative on this topic for y'all. So first I'm going to go into the history of nanofibers and what this all came from. So what is a nanofiber? We typically consider nanofibers as 1D structures. There's no depth, there's no thickness, there's no width. It's just a really long fiber. So the definition of what is a nanofiber depends on who you ask. Some people consider anything less than 1,000 nanometers or 1 micron to be a nanofiber. But some people say, it has to be less than 500 nanometers or, it may be even smaller. Are going down to like the 100 nanometer range or 200 nanometer range. What I always describe it as is when you look at nanofiber, it's about 1,000 times smaller than a piece of hair. And when people, ask, what does that mean? Obviously you can't see something 1,000 times smaller than a piece of hair. When you use electron microscopy, like the image I have up here, you see a piece of hair compared to nanofibers. This is a PTFE membrane. So you can see the hair is about 60 micron in diameter, and the nanofibers there then would be about 60 nanometer. So a lot of the interesting properties that come from nanofibers are based on this really small fiber that makes up the fiber mat. So where does the nanofibers come from? What's the history of this research? So the science of electrospinning goes all the way back to the 1600s, where they're observing how liquids behave in electric fields. And the cone-shaped deformation became known as a Taylor cone, just based on the researcher who first saw that phenomenon, where you see the droplets that form like in your sink or something when you're shutting off the faucet. If you put an electric field on it, it kind of develops a cone shape. And Lord Raleigh, English physicist in the 1800s, observed that this cone shape will eject droplets out. And then it really took off into electrospinning in the 1900s. And research set off where if you have polymers in there, you can see that those jets, the droplets that are coming off, actually can form fibers, and it pulls out the nanofibers. So when you have these polymer chains in there, when it gets drawn out, the chains kind of interlink with each other and just keeps pulling and pulling and pulling. And you end up with, theoretically, a consistent one fiber in a nanofiber mat. So each jet that's spinning, if it's continuous, will just make one fiber. It's pretty amazing to think about in these processes. So I know Jayesh Doshi is here, but one of the first papers, I don't know if I'm biased because of my Akron ties or if this really was where it all started, but we always considered Professor Renneker at the University of Akron as one of the leading researchers on electrospinning, and this paper came out in the mid-1990s and really took off a lot of the research that started with electrospinning and nanofibers. And then I always like to include a picture. When I was in grad school, I always liked putting a picture of my team that I worked with there. So this is from 10 years ago when I was in grad school. It's a really good time of my life where I got to meet a lot of people and really brilliant people in this picture and in the group that I worked with. So my advisor there is on the left side of the screen, Professor George Chase, who was really one of carried on a lot of Professor Renneker's work. Unfortunately, Professor Renneker passed away a couple of years ago. He was in his 90s. He had a really good life in his research, electrospinning nanofibers, and Professor Chase just retired in the last couple of years. He's got one more student that he's kind of helping get across the goal line and graduating into the industry. But these people in this picture, we've got people that work for Parker, H&V, Man and Hummel, got professors in that group. So a lot of people in the filtration industry came out of that research group, and you run into them in a lot of conferences. So what is electrospinning? So it's the main method of producing nanofibers in the filtration industry right now. Electrospinning is done by applying a high voltage to a polymer solution, and then the fibers are jetted, whipped, and drawn down to the grounded collector. So you see these fibers with that cone shape that comes from the droplet kind of cones out the other way. And then when you actually look at some of the pictures of what goes on during that process, it whips, and that's what's drawing it to the nano size, but also those whips are also whipping. So it's kind of a multi-dimensional whip that really draws these fibers down to that nanometer range. So it's really, really an interesting thing to look at when you can look at those high-speed images and really getting good resolution on it to see how this process is made. So the current production processes consist of continuous production, to coat the substrate with many jets. So usually you're not doing just a single jet. Obviously, you're not going to get a lot of fibers that way. So a lot of the production mechanisms are doing many jets or using some other, needleless or off-a-surface electrospinning. And really, why do we use nanofibers? There's some really unique properties to nanofibers that come from these nano-dimension structures. So you have a high surface area to the volume ratio. So basically, you don't need a lot of weight of nanofibers to have the effects on the property of the whole fiber mat. So you have more fibers for the time that you're putting down there. So you're not really measuring it like GSM or something like that with other processes. You're really, you can have a thin coating that's barely, negligible in terms of weight to the whole fiber structure, but it'll be, putting the properties on. And then you have high mechanical strength in nanofibers compared to others just because of that one-dimensionality. They're obviously, not able to stand on their own. You need some substrate, but you can get good properties of mechanical structure with nanofibers as well. And they can be highly functional. You can electrospin lots of different polymers, do lots of different things with them. We've done work in the research group on putting catalysis on there and looking at different ways of doing like catalytic converters. So we were doing research where we were making like little pucks that could go on like lawnmower engines. So you can remove the harmful gases from the exhaust on those more so than using the bigger honeycomb style catalytic converters and have the same amount of catalyst with a smaller filter element. And these fibers that I show here is something I did in my research. These are actually ceramic fibers, indium tin oxide for transparent conducting applications. So this is what it looked like. So I put it on my University of Akron folder to show how this transparency is. So when I deposited the nanofibers, I put them on the glass slide so you could see how opaque it was when you have a layer of nanofibers. And then I baked that glass slide in a furnace at, I think it was around 600 Celsius. And it converted those polymeric fibers into indium tin oxide ceramic fibers. And it kind of made a coating on the glass. And then I was testing the properties of it there. So you could see it made the fibers transparent, and then I could get electrical current to flow between the electrodes that I painted on to that slide. So really, really unique applications you can use nanofibers for different things. This was funded by a grant from NASA where they're looking at different transparent conductors for aerospace applications. And for air filtration, the really important property of nanofibers is this airflow, drag forces that you see in nanofibers. We refer to as slip flow. So when you have a large fiber and an airstream coming at it, if you're really into the physics of air filtration and airflow, you know that the velocity is roughly zero at the surface of, or any surface or a larger fiber. But the nanofibers are so small that you don't get a zero velocity gradient at that point on the fiber. So this allows better airflow properties through the fibers. And when you look at the mechanisms, what we know about air filtration and what you see in like the NAFA guide and what's probably on the CAFS exam and all those different mechanisms of air filtration, you see these air streams around the fibers and how The particles are captured either by straining or interception or impaction, those kind of things. So if you don't have that zero velocity there, you don't have as much of that eddy around the fiber, and you can capture more particles by mechanisms such as interception and that kind of thing. So you're really shifting that curve with all these mechanisms. So when I get into the next section, I'll show you how this really impacts the properties of the filter performance. But I figured I'd just give a little background on or a reminder of the physics of air filtration before I get into that. So I'm going to talk a little bit about the current state of nanofibers before I get into where I think the future of it can go and how we can use these to benefit everything in the filtration industry. So an easy one, being with AAF, we talk about the PTFE HEPA filter media. This is a nanofiber application where you can see a really difference in how filters perform with bigger fibers versus the smaller nanofibers. So you can see here on the left side, the pictures are the microglass, like a traditional HEPA filter media, and on the right side, you see the ePTFE type HEPA filter media. So the scale isn't the same on those top pictures. Obviously, I've got a really good zoomed in picture so you can see how those nanofibers impact the structure and how it looks more closely. Because if I had it zoomed out more, you wouldn't be able to see that structure as well. And then on the bottom, you see the depth of the filter media. So the glass, you have that depth mechanism. That's how the filter really works. But with the PTFE, you've got just the two support layers and then a really thin membrane in the middle there. And the benefit of using the PTFE is you can really get a much lower pressure drop and you can get the same filter performance with it. So looking at comparing a traditional box style HEPA or like the supply panel style HEPAs, as we call them, for clean rooms, you can see here for like the 11.5-inch deep filters, looking at the microglass, you got about initial resistance of 1 inch at the rated airflow velocity. And for the PTFE filter, the same configuration, you have about 0.56 inches, so almost half of the pressure drop. And looking at the media pressure drop versus the filter pressure drop, so you can see that the media and the filter, that difference is really coming from the media because the configuration is the same for the filters. So for the filter, the actual whole filter, 1.45 initial versus 0.7, and for the panel supply style HEPAs, you used to have a 0.53 inch initial resistance versus 0.27. So then looking at the MPPS curve, this is what I was talking about with that filter physics, how it changes. So when you have the different airflow properties of the filter, you see that the MPPS actually shifts to the left with the PTFE filter. So the MPPS of microglass media is usually around 130 nanometers, and it can get down to like 0.7, 0.8 nanometers with the ePTFE. So just showing, at different airflows, obviously if you increase the airflow, the efficiency will decrease a little bit. But comparing them directly, you see here, for the same grade of media, if you're using like I think this is H13 grade HEPA media on this, you can see that the microglass has a little bit higher MPPS. And that benefit to that is when you look at different particle sizes above that MPPS, the PTFE will always outperform it because as that efficiency rises, you already met your lower minimum point sooner. So that's the benefit of using these PTFE medias in HEPA filter applications. Another interesting application I've seen is looking at bag filters, looking at microglass versus a synthetic media with an EP or a nanofiber media. So you can see here comparing same configuration or 22-inch pocket filters with 10 pockets. Looking at the microglass on the left, the synthetic nanofiber on the right. We had this filter that it had comparable, maybe a little bit lower by 0.1 inch initial resistance, and it had similar dust holding properties because of the way the media was manufactured. So the media that was made for this filter was really an interesting extended surface area type media. There was, it wasn't just a straight coated nanofiber media. They really designed it well to have a good upstream dust holding performance as well as having the nanofiber there for the efficiency. And you could see for similar mechanical efficiency, you had a lower pressure drop, and they were able to design this media to have a same dust holding capacity roughly. And this would have passed an Appendix J test. It would not be electrostatic charge. It wouldn't decrease in efficiency. So these are ways that are really good at using nanofibers to develop better products in the market.
Are your air filtration personnel NAFA certified? ask if they belong to NAFA and have their Certified Air Filter Specialist or NAFA Certified Technician designations. The CAFS and NCT designations are earned after rigorous exams and demonstrate that the air filtration professional has a high degree of knowledge and professionalism. To learn more about NAFA certifications, visit nafahq.org.
However, it isn't always positive. Looking at, this is a MERV 15 media that we evaluated with nanofibers, and you can see the main thing pointing out is the dust holding capacity. It took us 4 grams of dust to reach our final loading point at that point, versus a traditional MERV 15 media with electrostatic charge on it. So that's something I think we need to overcome. I think different test methods or different applications for the fibers can boost that dust holding performance, but I'll talk about that in a little bit more detail. But why is that? Why do we see that difficulty in performance compared to other traditional like MERV 13, 14, 15 type medias? And it's the electrostatic charge. It's something that's kind of always discussed in these talks and in different forms where we know that the electrostatic charge is present, and that a MERV 15 filter with electrostatic charge might not actually be a MERV 15 filter because the electrostatic charge is pulling the particles out of the air and attaching them to the fibers. It's going to degrade in performance over time. And the nanofiber media, again, we took that PTFE and we loaded it with dirt. And you see, I try to explain to people that a nanofiber substrate is basically, it's considered a membrane. It's like a wall. It's not depth loading. It's designed to just catch stuff and not let it go through. So there's no depth to it. You can't really have a dust loading performance with it. So we need to design better media with better dust holding capacities above that nanofiber. And like HEPA filters obviously aren't designed for dust loading applications. If you're in a clean room, for example, maybe in like an air handler HEPA filter, you'd want a little bit more dust holding capacity. But we'd always recommend people to use better filtration upstream of HEPA filter anyway. So the electrostatic charge, you have that MERV 15, but we know with Appendix J that MERV 15 is not going to always perform as a MERV 15. And this is actually the one filter I'm showing here actually dropped to a MERV 13 after Appendix J test. So we're loading with the fine salt particles. You're not getting that true MERV 15 performance. So it's with any electrostatic charged media. If you're going with a MERV 13 filter that has a low pressure drop or anything, you're going to eventually lose that efficiency and not have that performance. So if you're looking for a MERV 13 that'll stay a MERV 13 forever, we have to look at different options. So nanofibers is going to be a way that we can hopefully get to that and bridge that gap between the performance that we want with like these MERV 13 electrostatic charge filters, but aren't currently getting. And then ISO 16890, they use an IPA vapor discharge. So it might be another thing that was discussed and has been brought up in previous NAFA meetings. But you see here, the electrostatic charge, it drops from one filter class to another based on dissipating the electrostatic charge. And what they actually do is they average the initial state and the final state after it was discharged, and you can get a average efficiency with that. So I think it's good to make people more aware of what's actually going on in these filters and how the filter media efficiency isn't actually what it's advertised to be always. So once we have more awareness of people knowing what's actually going on with these filters, then it'll spark that development of these nanofiber medias and maybe give us more of a reason to focus on these new technologies that are emerging in the industry. And then again, dust load. So when you look at the initial resistance and the dust loading capacity, so we tried to boost the efficiency of like a MERV 8 filter with nanofibers. And you can see here we almost doubled the initial resistance, so you're getting better mechanical performance of the filter media, but you're also taking that dust holding capacity and significantly reducing it. So it's really about finding that balance between what's going on in the filter and the mechanics of what's going on, and trying to get a better benefit of that, of everything that you're looking at. So the reason for this, and again, reiterating it, these mechanical filter media like microglass, have a depth loading region so you can see the dust load sieve through the filter media, and the membrane is kind of just like a wall. It's just face loading it, and then you're going to have an increase in pressure drop based on that. Other challenges we've seen in nanofibers is just inconsistency in what we receive from the process. Because of nanofibers, the electrospinning process, it just sometimes you need, if you put just a very fine layer of nanofibers on there, it can sometimes get damaged or pulled off during, I don't know if it's in the rolling or shipping or manufacturing of the pleating the filters. But depending on how you're using the nanofibers, you can have difficulties with these. In these pictures, there are nanofibers in them. You can see those little branches in between the fibers. Those are the nanofibers that were deposited and were removed from it. So we've seen some inconsistency from certain people, and there's other people that do it well. So when you really, the stuff I've seen that is really successful is the stuff where they build the nanofiber on a more rigid structure instead of just depositing it and coating it on an existing media. So when we had this feedback that we had seen some issues with the nanofiber coating, then we got better stuff back where you could see more nanofiber coating. So this is an example of one where we saw some poor coverage, and then we had some feedback. And then the one on the right, you see a really good nanofiber structure on there. So it's really about, as we learn more about these processes and want to use these media, just making sure we have the right application of the nanofibers on the substrate. So what's the future of nanofibers? This is the exciting part. Where can we go from here? I think testing is the big thing. So when you're testing a filtered dust loading with ASHRAE dust, that's really going to cause a disadvantage to nanofibers. I've seen, we see the dust reports, and we know that ASHRAE dust is what we have for the testing. But I've not heard someone say that, this nanofiber media has 4 grams of dust holding capacity, but they're not changing out their filter every day or every week when they use it in application. The filters are perfectly fine to use for a normal life cycle of a filter. So they're not seeing the type of dust loading that we do in a test. And ASHRAE dust is really unfair to nanofiber medias, I think, is what it ultimately comes down to. So ISO 6890 normalizes the filter efficiency to an urban particle size distribution. And I know there's some issues with that mechanism and why they do that. But the point is, when you look at the particles that are in the air, you have an ultra-fine particle range and you have a larger particle size range. And that's just how outdoor air is made up. So when you look at what dust we're testing the filters with, it's all that large particles. We don't have a lot of the ultra-fine particles in the test dust. And that's going to cause an issue with how the filters are tested. In ASHRAE dust, you put cotton liners in there. So you're putting even more big particles in with the ISO fine dust, and you're exacerbating the issue, basically. So I think if we have a better way of testing filters, it could be more favorable to showing how nanofiber medias actually perform, and then we can get a more traction on that in the industry. So at Purdue, currently, research is funded by ASHRAE. Hopefully the data should be out soon, but they're making urban aerosol, they're using a thermal flame generator with a salt rod that's creating a really nice particle size distribution. So you're loading these fibers with more particles that would more represent what's actually in the air and what these filters are actually seeing. And these particles could do a good job of measuring that efficiency loss because you're coating with the fine fibers like the Appendix J, and you can see how that efficiency is being affected over time. And I think this is really going to be a game changer in the filtration industry in the next couple of years, where you might see new standards being developed based around this new aerosol, and you can see the benefits and disadvantages of certain filter media technologies. And I think it's really going to take off and cause a change in what's happening. The ISO 6890 standard already requires them to discharge every single filter with IPA. In the U.S., we don't really we don't mandate Appendix J. We don't mandate that minimum efficiency to everybody at the current time. So once we have different filter test methods that will show the worst case scenario performance of a filter, then people want to know, well, how do I make sure I have a MERV 13 filter that beats MERV 13 and stays MERV 13 for its whole life? And nanofiber is a great way to do that. You can have lower pressure drops compared to other large fiber technologies like microglass with that. And you might be able to get there in like a 2-inch filter that you might not be able to in current applications. So I think that's going to be the big change coming up in the next couple of years. And then, the future is also kind of what's going on now is how we improve lower efficiency media with nanofibers. Ignoring the dust load part that I talked about earlier, because I know that that's kind of a function of poor test methods right now, and the ASHRAE dust not really being applicable to nanofiber medias. But you can take a MERV7 media, so this media that we tested before and after nanofiber coating, and we boosted up to a MERV11. And you can see the pressure drop, does go up by a factor of 2. You're doubling your pressure drop, but you're getting that efficiency performance that you're not getting. So as people get more aware of what's in the air and how they want to protect their spaces with people, you want to look at how we can improve that. So when you compare this MERV7 nano with electret media, you can see here, the pressure drop increase is a little bit higher. You've got 0.3 for that electret media and 0.4 for the nanofiber media. But we know that MERV11 with electret technology is going to drop to MERV9, MERV8, MERV7, and that nanofiber media will maintain that efficiency throughout its life. So as we have the benefit and make people more aware of what's going on with the filters and the electrostatic medias, I think nanofiber will become more appealing to people. And then they might, if that pressure drop delta is not too significant and the cost delta of the filter is not too significant, then we can really make a change in the industry. And there's lots of work going on and production capability. So, as people get more drawn to nanofiber medias, there's going to be better ways to make the nanofiber medias. And there's I pulled this picture from an El Marco machine. But it's just one company that's making mass production of nanofiber machines. You can see a lot of the stuff's coming from not from the jets and needles like I was doing in grad school, but from electrifying surfaces and depositing the polymer on there and creating the electrospinning that way. And having more jets and more we'll be able to cover more of the media, and you can get more nanofibers coating the media instead of if you have to slow down the line to have more nanofibers deposited, maybe you can run the line faster and you get more efficient and you can lower the cost that way and drive better performance of the filter medias by improving nanofiber technologies. So I know like El Marco is one particular company that was making commercial electrospinning nanofiber equipment that anybody can just buy and put into their plant or lab or whatever. But a lot of the companies making nanofibers have their own proprietary things that they're working on themselves, and they have their own nanofiber electrospinning experts that are designing equipment that's not going to be able to be seen in commercial applications. So to wrap up everything and to really put a bow on this talk about nanofibers, I want to put a emphasis on that fine particulate. When you look at the makeup of the air, you see about 97% or whatever of the amount of particles in the air is in that ultrafine range. But by weight, it's shifted towards the large particles. So the 30% of the weight makes up 3% of the makeup of the air. So really, there's a lot more fine particles in the air than what we're aware of, or more than we can count. It's a mind-boggling number. So when you look at something like different size distributions, the count number you measure with the SMPS, you see on that top curve, you have to get really high-tech particle counting tech capabilities to measure how much fine particles are in the air compared to everything else. When you get to the optical particle counters like we use for the 52.2 test, you're not picking up anything until basically 0.2, 0.3 micron. So the majority of the particles live below where we can even detect in the current test methods. Except for HEPA filter, we use SMPS and photometers and that kind of thing to detect those fine particles. But they're in the air, and these are what cause the damage. But the health impact of the small particles is something that we can't overstate. A lot of effort was put on clean water before, because if you open up your faucet and you see brown water, you're not going to drink it. You don't want that in your system. But if you have a cup of clean air versus a cup of dirty air, you're not going to know the difference until it's too big of a problem. The harmful air quality is not something we can see, and when you can see it, you're beyond the point of it being bad. Like when they had to shut down Beijing for the Olympics to make sure the air quality was good enough for athletes competing at the peak of their health. So we can't tell the difference between clean air and dirty air until it's too late. This is something that's always stuck out to me when I was looking at the internet and I saw a 9-year-old little girl in UK, they put on her death certificate air pollution. That was the first time they put air pollution because they couldn't find any other reason for how an otherwise healthy kid would die like that. And Ella's Law in the UK was being established to make clean air as a human right, and that's still, I don't know if it was adopted yet or still going through the legislation. But it's something that's being aware, and I think as people become more aware of these issues and health problems that come with dirty air and COVID and the viruses and everything, and people want to upgrade the filters in their systems, we got to do better, and we got to find a better way to deliver the products that will actually have an impact. So using electrostatic media that will lose efficiency and not perform the way that it's supposed to. If everything's shifting to MERV 13, we want to be able to provide someone with a real MERV 13 filter that we can guarantee them that will be MERV 13. So with that, I'd like to thank you for your time and listening to me talk about this.
What is the potential for nanoparticles coming out of the filter with the nanofibers? Is there a possibility of shedding at all or not?
I haven't looked too much into that, honestly. I know with the HEPA filters with like the PTFE, I mean, those are, we don't see any issues with that. So I guess as we drive better performance, we'll look more into that. But I think using nanofibers is better than, not and having other issues with filter technologies that are out there. Thank you.
Thanks for listening to the Talking Air Filtration Podcast, a production of the National Air Filtration Association. Clean air matters.